Because space is expanding, we never reach it. But that future bubble is the future hologram. Are we sure?
Okay.
Okay, so basically, if we look into a past, we can only look a certain distance into a past, and it looks like we're in the center of this distant bubble. Okay? Now, when we look with our telescopes, we're only seeing the past. However, our influence is coming from our future. And they're coming from this future bubble. We're at the center. That's a sphere around us. Now, at any particular moment of what's called, if we take the Hubble flow, it turns out because the universe expands, we can define a kind of cosmic simultaneous surface, and that we are a finite space-like distance, instantaneous distance away from that sphere. Okay, but what's happening is that we have what's called the future light cone. And that future light cone is if we send signals out to the future, if we radiate signals, those signals will arrive at that distant sphere at a certain finite time. Okay, and at that time, that sphere will have a certain radius. But here's the thing. What it looks like, it turns out that future event horizon, that future spherical bubble that's surrounding us, but it's surrounding us in our future, not, okay. That future sphere has a certain area to it. The sphere has a certain area. And if you compute the area using Tamara Davis's figure 5.1, I think is where she computes the area as time evolves. Okay, and if you take the reciprocal, 1 over that area is like a curvature. It's called the de Sitter curvature. 1 over that area, you multiply it by this Einstein factor, which is kind of like a string tension. It actually correlates with string theory. We call it string theory tension. So string theory tension is an energy divided by a length multiplied by 1 over an area, which is energy divided by volume. Guess what you get? You get the observed dark energy density today.
Wow.
Okay.
Now this was totally unexpected.
Well, yeah. In fact, most people don't even know it. I mean, this is Jack Sarfatti telling you this, basically. They don't, I mean, she doesn't actually say, I don't think she says it in her thesis. I have to look. She doesn't talk too much about holography, I don't think, but I have to look. It's a big, long thesis. But here's the thing. So what this is saying, now, turns out that if you plot the area, okay, now there are 2 areas involved here. I mean, if we are at our present moment now, we can mathematically we can look at the area of that future bubble simultaneous with us now. But I'm talking about the future area of that bubble. I mean, that's when light signals, advanced signals coming from that future bubble reach us in our present now through the advanced Wheeler-Feynman effect. Okay, it's that area. That area gives us the observed dark energy density today. It's the future area at the intersection of our future light cone with that bubble, with that future event horizon. By the way, the future event horizon the future event horizon is the past light cone of the omega point, which is like the end time of the Bible. It's like the end time. It's actually an infinite clock time, but it's what's called a finite conformal time. But that's a whole, these are mathematical subtleties that it's hard to explain to a popular audience. But it turns out that this explains irreversibility, explains the arrow of time, explains why we age and why things tend to go, why complexity evolves one way and why we get old and die. Because here's the thing, if you look at Tamara Davis's figure 5.1, what happens is that the area of our future horizon at the Big Bang in our past is very small. It's very small. So if you were to compute the dark energy density then, it would be much bigger. We'd have a huge dark energy density, which is what happens. That's inflation, huge dark energy density. But as the universe is expanding, the area of that bubble is getting bigger and bigger and bigger. And it quickly saturates. It approaches sort of a constant value. And we're living in the region where it's pretty much constant. This is called the de Sitter solution. It's a solution of Einstein's field equation. It's all a self-consistent thing. So the area of that future horizon more or less stays the same, which is why it looks as though the dark energy density is more or less the same. But here's the thing. This is the Sarfatti insight now. The dark energy density we measure today depends upon the reciprocal area of our event horizon in our future, namely when our future light cone today intersects that future horizon. It's all very clear. If you look at Tamara Davis's figure 1.1, what I'm saying is actually very simple. It's like Euclidean geometry almost. It's like triangles.
Does she provide any chronological information as to when this future horizon is going to happen?
No, it's happening now. It's happened since the beginning. We always had a future.
We've always had it. Okay.
We've always had a future horizon. It's different. We had past horizon. We have a future horizon.
I see.
It's there with us all the time. And what we imagine a world line. We imagine that we're immortal creatures, the immortal gods. That we're there. We imagine we're there from the beginning of the universe, the alpha point to the omega point, and it's like this infinite world line. Now it turns out that different observers all have different alpha points and omega points. It's observer dependent. This considered cosmology, observer dependent. It's kind of like Leibniz's monads. It's a little bit like that. So in other words, if you're on a very distant galaxy, you're going to have do your own construction. Your future horizon is not identical with my future horizon. We'll have our own. We'll live in a little bubbles, so to speak, a little Leibnizian bubbles, a little monad, so to speak. But they're very close. But it turns out you have to look at Max Tegmark, what's called chaotic, eternal chaotic inflation. It turns out that if what Max Tegmark calls a level 1 universe, we're all in the same bubble. We're all in the same inflation bubble. Then the numbers will be the same. The dark energy densities will be the same even on Alpha Centauri or some distant galaxy as less, because we're all in the same bubble. If we're in different bubbles, it'll be different. That's called level 2. Okay, we won't go into all these details, but if you Google Max Tegmark multiverse, you'll see this picture of these different levels. It gets pretty complicated. But it's pretty. It's a pretty picture is emerging. So, what I'm saying, so this is an advanced effect. The dark energy density we measured today is a fact from the future, effect from our future horizon, the area of our future horizon in our future. Okay, now it also turns out that this future horizon plays the role of the wheel of Feynman total absorber. So the wheel of Feynman theory becomes consistent. But there's more to it than that. It turns out that this future horizon now we go into what's called Hawking radiation, the Bekenstein theory. What happens is that the area of this future bubble, this spherical, we're in the center of the spherical surface, but the spherical surface is kind of in our future. The area of that thing is quantized as a quantum of area, like what's called loop quantum gravity. The area is the Planck area, like 10 to the minus 66 square centimeters. That area, it's like a pixelated, it's just like, and there's information, there are quantum bits. Each area is like a quantum bit of information. Turns out there are